Swayam Prabha. Digital India. Educated India.
Hello, good morning. Today we are going to discuss a very important application of vacuum technology in our day to day life, that is in chemical and pharmaceutical sectors. We have lot of necessity for varieties of chemicals in our day to day life. Of course, everything is a chemical, every material is a chemical, whether it is a fertilizer or a small pill that we take, or whatever that we are eating, even food is also a chemical, and varieties of materials that we use, including the face powder or cream, everything is basically a chemical. And pharmaceutical is also chemical. In fact, pharmaceuticals are a subset of chemicals, and chemical is a very wide discipline under chemistry. And we are not going to discuss those aspects today, because not much time, it is a big field by itself. What we are going to discuss today is application of vacuum technology for chemical and pharmaceutical process industries. In this, we are going to cover the concepts like vacuum distillation, and little finer vacuum distillation is called molecular distillation, then drying under vacuum conditions, then freezing and then drying under vacuum conditions, deodorizing it, certain things which we do not like such smell, how to do that using vacuum, increasing the speed of production by vacuum filtration in industrial atmosphere, and conveying various products using a vacuum duct along with a laminar flow of air, so that fine particles or whatever products, they will be conveyed from one end of the process to the other end. So, all these applications utilize vacuum for various sub components. Like in a conveying, we are trying to use force application. Okay. In a drying, we are trying to use the concept of reducing the boiling point of water to room temperature. So, that process can be started at room temperature, we can remove water easily. In a distillation, when there is a mixture of 2 or 3 constituents, high volatile and low volatile compounds, etc., depending on the relative volatility and all these things, chemical engineers know very well this terminology, and how do you separate them using distillation columns, and how do you convert that distillation column into a vacuum distillation column, what are the advantages. These things we will try to see in this lecture. And similarly, instead of simply drying, you freeze it, spending some more money in freezing it, and then drying not from the liquid phase, from a solid phase. So, there we are trying to use sublimation concept, somewhere we are trying to use evaporation concept, sometimes we are using a equilibrium, vapor liquid equilibrium concept type thing. Mixture is gaseous mixture, vapor mixture and liquid mixture. So, naturally certain things get rich in high boiling point, high boiling phase, and other thing gets richer in low boiling phase. These things are very well explained in several articles in Wikipedia if you go under distillation concepts. In fact, lots of books are there on distillation. The concepts are same for vacuum distillation also. So, directly when you get into the subject, left side you can see a typical column. In refineries they call it as vac column, and in vacuum we are getting certain advantages, as I already explained you. I am not going to into the details of distillation concepts, because it is a big field, and also most of us are aware somewhere or other in our college education or school education, depending on the boiling points, different components will go up and condense, and it is like evaporation, condensation at various phases, keeping them intimate contacts with vapors and liquids in trays and packed columns. This all vacuum distillation concepts, but instead of heat energy, we try to give the pressure drop created by a vacuum on top of the column. If that is the driving force, then it is called vacuum distillation. What do we gain by it? We need not heat much. Temperature increase is not always good for process also. In body, if you get temperature increase, we get fever, that is not good. Similarly, in chemicals or pharmaceuticals, all the more, they are very heat sensitive. So, same separation from a raw materials, if you can separate various constituents, that is the basic of chemical engineering, basically to separation science, that is called. And if you can do it without heating, it is good. On one side we are saving energy, on the other side the decomposition is not taking place. We will see when we go into pharmaceuticals, it is going to be very important. Decomposition should not take place. A long chain molecule in a drug is a drug, and when you are heating it for distillation or some other purpose for separation, then it may get cracked and it becomes two pieces, the molecules, long chain molecule. A short chains may be dangerous, it may be sometimes poison. So, processing heat sensitive pharmaceuticals is very important. In certain chemicals also it is very important. These chemicals can be even some edible oils, etc. They are also basically chemicals, though they are food related items. So, vacuum distillation is playing an important role in refineries, particularly for oil refineries, etc., where we try to use the depression of boiling point as well as creating a driving force in a column by pressure drop, by sucking principles instead of heating in the reboiler. Bottom is always, bottom of a column is always called reboiler, top is towards condenser, various trays. I am not going to discuss that, and that will take 10 hours, and it is easy for you to understand from very good books, where you can get a very elementary introduction of distillation. So, I leave it to you. Basically, distillation of a liquid under reduced pressure, it will enable the operation at low temperatures, because boiling takes place at low temperature. The basic principles of distillation are not changing, it is same. Vacuum distillation is more or less same as normal distillation principles, but the driving force is vacuum, not the heating. And vacuum distillation is often the only feasible means purifying very heat sensitive materials, where you cannot afford to have high temperature distillation columns. It avoids undesirable reactions, thermal degradations, polymerization of process materials. Sometimes this thermal energy may polymerize the thing and we get some other product, not the products which we want. Okay. So, normal distillation is ruled out at that special situations. There is another thing very important in chemical operations. When we plot the vapor fraction as a function of liquid fraction type thing, y as x ith component. I will not go to the details of it, but this sort of diagrams you will see in chemical engineering separation science books, and these curves are popularly known as equilibrium curves, and the equilibrium curve, if it is a ideal thing, it will be a 45-degree line, but in a non-ideal nature, So, always vapor will be slightly more compared to the equivalent liquid at the same temperature. So, there is a bowing taking place. Under vacuum operations, if you try to do this in either boiling or heat transfer, boiling or what you call distillation or drying, of course, heat transfer is also associated with that, and mass transfer is also associated with that. It is a very complicated picture. Many people do a lot of PhDs in this line. Under vacuum, the thermodynamics will dictate that the bowing will be towards top side, and it is increasing towards top, the separation efficiency always increases. And if it crosses the 45-degree line, which is very dangerous, because it is not possible to purify beyond this line, because there the thing is approaching ideal. So, the vapor fraction and liquid fraction is equal, because they are touching the diagonal, and you cannot get purification beyond this point. This problem is known as azeotrope formation. This happens in certain chemicals, and under vacuum, luckily this point shifts to this point. So, that way you can get purity almost up to this point, pure vapors you can create. That means, the azeotropic thing is eliminated under vacuum. On one side low boiling point and other things are there, vacuum is the driving force, heat is not the driving force, but if it is azeotropic mixtures, it is all the more advantageous. Azeotrope is released, it is not at all there. So, that way the separation efficiency even under theoretical considerations, it is much better under vacuum considerations. Okay. So, mixture separability is very high in general under vacuum, and it is all the more required when azeotrope formation is taking place. Okay. And thermal degradation, all those things go always hand in hand. If you do not have to bother much of thermal degradation, you can have normal distillations, okay. But purity levels cannot be very high, but production rate may be high. And in vac columns, you will find another important aspect, density is less for the same mass flow rate. So, the diameters, the volumes will look big. For the same production rate, at the end of the day, distillants are separated components. For the same production rate, the column size will be bigger under vacuum. So, that way you make these columns, which has to withstand vacuum, the mechanical considerations, thickness of that, and pumping speed calculations. Similarly, in the vacuum system that is connected to the top, the piping network, conductance calculation, all that has to be done. Okay. Similar thing I am trying to show in another case, where it is a pharmaceutical sector. Typical vacuum pump, it is boosted by a booster pump and with an intercondenser. So, that under this pressure some of it can be liquefied and it can be drained, otherwise that water vapor or something can go into a rotary vane pump, which is not good. Here it is a vapor phase. By the time it came out of the Roots blower, it might be semi condensed phase, that condensed thing, or it can be condensed with a forced condenser, and that way some part of it can be removed. And these things are coming from here. So, there is a condenser here and there is a vacuum, which is the driving force, that is finally connected to the condenser into the column. The vapor is getting sucked. Always vacuum pumps are connected to the top of the column to handle the vapors, and from the feed is always given at the center. The top side, it is a rectifying section and the stripping section. Stripping, scrubbing, rectification, enrichment, these are all various terminologies used in pharmaceutical and chemical sectors when distillation is being discussed. And refluxes, sometimes out of the product, some product has to be sent as a reflux through a pump, because the flow rate has to be adjusted in such a way, the vapor liquid equilibrium is forcibly made in by various trays or packed columns in such a way the purity of it increases. Though we lose some product again going back into the process, but the purity can be increased. This is a standard method called reflux mechanism. There can be reflux mechanism in the reboiler side, bottom side, there can be top side, and here we need to condense them and again supply it. Similarly, here also, here the reboiler, some portion of it can come here, that thermal energy can be given to the fresh feed again and it comes out as a bottom product. So, there is a top product, bottom product, accumulators, condensers, refluxes, vac columns, trays. This is a standard terminology. I am not going into detail, though I have explained little bit to you. I hope you got some idea. So, in pharmaceutical industry, it is widely used distillation as well as vacuum distillation, and typical processes like solvent recovery and recycling, purification products, that is for real selling the product, and sometimes byproducts are there for waste minimization. All this goes into unit operations in a typical chemical or pharmaceutical plants. We will not go into detail, but it was understood by the chemical engineers, by adding this vacuum into this stage, you get several advantages in the purity levels as well as the operating temperatures, so that corrosion will not take place and decomposition will not take place. Okay. So, stripping and in the rectification column, all these things go very nicely, smoothly, but of course, volumes will be bigger, but without any degradation or decomposition, and you will get top and bottom products. Maybe little slow process, but you will not get any degradation or decomposition, which is very important in pharmaceutical sectors, costly pharmaceuticals. That is why vacuum distillation is playing an important role. And recently, with the pollution control board putting lot of constraints, you cannot throw out the vapors from the top side of it column into air. So, it should be a closed loop. That is all the more reason vacuum distillation is getting more and more popular. Okay. The vacuum boosters have to be designed in such a way, it will have sufficient throughput to handle this vapor under continuous feeding conditions, and it should maintain that particular vacuum where the saturated vapor pressures of that liquid, whatever that comes out, is to be like that, it will convert automatically into vapor phase, because vacuum is coming there. So, even at lower temperatures it will be vapor, all that you have to maintain, the instrumentation aspects have to be looked into it. So, there is a lot of process control that is important in such operations. I am concentrating more on that. So, that is vacuum distillation, and an extension of vacuum distillation, instead of distilling vapors, if you try to distill molecules, that means distilling means what? Evaporation, condensation. But if you are evaporating, instead of vapors, a vapor means vapor, instead of that, a molecules are stripping out, coming out, because of they have overcome the forces from their liquids, and they come out and then directly go to the condenser, and the distance between the source and the condenser is adjusted less than the mean free path at that operating vacuum level, then it will not be hit by other molecules. That way, we will get distillation molecule wise. The purity will be very high, but the rate of distillation will be very slow, but purity is very high. There are certain very costly pharmaceuticals where we try to use molecular distillation. It is becoming more and more popular in the recent times in pharmaceutical sectors, and it is here we need to operate the columns in 10⁻³ torr. They are more called as stills, molecular stills, okay, because they are relatively small, but they handle very costly products. 1 kg may be costing 10 lakhs rupees, because it is a very sensitive chemical, pharmaceutical chemical, and we need to separate them very carefully, and there are certain things they have got very low vapor pressure. So, unless you go to the pressure less than that vapor pressure, it will not evaporate. Such problems like fatty acids, esters, monoglycerides, vitamins, paraffin fats and polymers, or oils or fish oils, when handling such things which are heat sensitive products. So, we need to reduce the boiling point, and they are so heavy molecules, their vapor pressure is also very small. So, if you want to create a vapor, they may have to go to very high temperatures, then that is dangerous, because they are heat sensitive also. Decomposition takes place chemically, physically you may get vapor. So, that is not allowed. So, for that your pressure on the top of that also will be less than that particular vapor pressure. That is why it is called molecular distillation. When you reduce so much, the distance between condenser and the source will be definitely less than the mean free path. So, that way even whether we want it or not, distillation is always molecular at 10 power minus 3 torr. So, molecular distillation is an automatic consequence of reducing the pressure. The reducing pressure is done because there are certain heat sensitive chemicals which are heavy molecules whose vapor pressure is so less, unless you go to a pressure less than that it will not evaporate. So, all these things together is creating a very good application called molecular stills, which are coming up in creating vitamins, oils and fatty acids and glycerides and plasticizers, etc. They are very important in biochemical industries and pharmaceutical sectors, particularly this type of heat sensitive products. How it is done? Well, from a material which need to be distilled, it is little preheated after a flow meter, and it is little heated through this, and some bit of degassing can take place here itself using a vacuum pump, because at every stage you need to put some vacuum and reduce it, certain things can be removed, and whether you remove it totally or not, it is up to you. You can put a condenser and keep it, that itself may be a byproduct, and then remaining that liquid distillant, okay, which is still to be distilled, that will fall on a wide surface area, big surface area, a candle type of thing, which is internally heated by an electric heater, and it is covered by another cylinder which is condenser basically. Through the same condenser you connect it to a fine vacuum pump operating at minus 3 torr. The gap between the source where the liquid is falling like a film, because it is falling on this, the film, it evaporates. Film is creating a surface area, wide surface area, but the vapor molecules are travelling this much distance only to reach the condenser, which is very small. So, it is basically molecular condensation, because molecules are travelling from here and they are condensing instantly there itself. The path is much less compared to the mean free path at this vacuum level. So, this is called a molecular distillation using falling film molecular still. You can increase little bit temperatures, so that vapor pressures are little more. You have to adjust the process parameters. Instead of keeping a simple static evaporator, you can create a cone type of structure. This is called centrifugal molecular still. This is called falling film molecular still. You will find several such things nowadays in advanced pharmaceutical laboratories. Quantities are less, vacuum levels are very good. Here the thing that is distillant is yet to flow here, and it is a rotor rotating at high speed, and it is a conical structure. Because of centrifugal forces, it will form a thin film, and quickly this distillant comes here and gets collected here, and through this the distillant will be going out, and during this process this film, that particular part of it, whatever is to be distilled, that will evaporate, and this dome will act like a condenser, and that condensed portion which is called distillate or condensate, it will be collected from here. Whereas the other thing which becomes enriched, because other thing has gone out, now that will be collected distillant. So, sometimes both of them are products, or again recirculate it like that. So, this is another picture, and I have written everything here. It is rotation is going on because of to create that force, centrifugal forces, and it is spreading uniformly, and that distillant is collected. There is small amount of radiative heaters here to adjust the temperature of these things. Heat transfer, then mass transfer and film formation, evaporation, collection of distillant, collection of distillate, and all these operations are to be done along with vacuum pump, because entire thing is connected to a vacuum pump 10 power minus 3 torr, and it is molecular distillation, because the distance between this and the condenser is much less compared to that. While it is dynamic here, it is static here. It is called falling film molecular still, it is centrifugal. Well, lack of time, I will not be able to go into details of this molecular distillation, but they are very interesting topics. So, next operation which is done under vacuum in chemical industries or pharmaceutical industries are simple vacuum drying. I have written here very clearly, you can go through it. It is a laboratory type of ovens we can see in most of the laboratories in chemistry, even in school. But these ovens are vacuum tight ovens. There is a gasket here, there is a window here, and you can keep whatever you wanted to dry, you can keep it. Drying means removal of water most of the time. There can be special cases, and that dried water vapor can go through the condenser here, and comes into the condensate, and the other dry air etcetera is taken out to create the vacuum force, and these vapors are continuously getting collected. The condenser will condense water vapor, the dry air will go to the vacuum pump. Dry air going out means it comes through various leaks etcetera, and vacuum pump is the driving force for sucking these vapors, and vapors are sucked heavily, the remaining portion gets concentrated. This is called vacuum oven for drying certain pharmaceutical liquids. And if you see this chart, boiling point of water at various pressures, you can very easily see at 30 to 60 millibar water boils at 25 to 35 degrees centigrade. For example, if I connect a small vacuum pump here, and if I put 30 millibar, which is nothing, very simple pumps can create, water boils, I do not have to heat it. So, that is the advantage, we can put it in vacuum. If you want, you can keep some heating here. In industrial atmosphere, we keep steam heating from the waste steam. In small laboratory scale, we can put an electrical heating here through conduction and radiation, because in vacuum there is no convection, heating is going on. So, different trays can be handled here with a perfectly airtight door, and rotary vane pumps, dry screw vacuum pumps, water ring pumps we have seen earlier, all of them can be used here. When you use water ring pump to remove water, the water that is used as a sealant liquid in the water ring pump should be very cold, because its vapor pressure is much less, then only it will work like a pump. So, those precautions you have to take into account. Basically 1.5 meter cube type of capacity with 20 shelves, these are commercially available, vacuum drying. Then freeze drying, instead of simply drying from the liquid, you convert that liquid into solid by cooling it and putting a pressure below a particular pressure. The critical pressure and critical temperature, sorry, that the triple point, there is a particular pressure and particular thermodynamically particular temperature and particular pressure. If you can bring it below that, then the material to be dried is in a solid state. So, under vacuum of that level, there will be direct transfer of gases under sublimation from the solids to the gas. So, this is done by freezing the material below 0.01 degree centigrade, which is a typical triple point of water. This is the phase diagram of water, and low pressure, which is 0.6 kilopascals. If you can bring it below that, then you are in a situation in the solid phase, and solid to gas type of equilibrium you are talking, that is through sublimation. Because of lack of time, it will be difficult for me to explain in detail. You read it, and this is nothing but having some condensers near to the pump. There is another condenser to cool it or pre-cool it, and vapors under cold condition they are taken out and they are condensed here, otherwise it will enter into vacuum pump. This type of commercial freeze dryers are available for various capacities, utilizing rotary vane pumps or screw pumps etcetera. Basically, idea is to freeze the product and use sublimation instead of evaporation for drying operations. It is also a dryer. Then one major application which will increase the speed of production in a chemical industry or pharmaceutical industries, very simple application. Using a small vacuum, filtration speed across the filter paper can increase. This sort of structure you may be seeing in school laboratories, but in an industrial scale a drum filters are used, and a slurry that is coming from the industrial product, which is a feed, and the fine water and some gases, whatever vapors, they can be sucked through this filter in a drum, because a vacuum pump is connected to that, and these liquids when they are inside, because of suction across this, the remaining portion gets concentrated, very hard slurry, and that will be a product. In the process we have concentrated this one. So, this sort of vacuum filtration increases the speed of filtration. We have to filter in certain operations in chemical and pharmaceutical, but that is if you use only gravity principle, there is a particular speed of filtration. But if you try to use vacuum, it helps, it assists the gravity, so that speed of filtration is high. So, it is a typical application. The photo shows here a vacuum pump is connected in the receptacle after the filter paper. In a large scale, in industry, it is a drum filter with this vacuum pump. The last application in the chemical and pharmacy applications is vacuum conveying, which I already told you. There are various products and sub products or waste products, etc. They need to be conveyed to a safer distance using belts which are there in a vacuum or even floating under air molecules, they will be conveyed. So, all these things are being designed in a very fine fashion using vacuum conveying, because the Food and Drug Administration, they give some guidelines and clarifications, because you cannot handle things with hand. Even when you try to send it to the next operation in a pharmaceutical sector, all this transfer is done using a vacuum conveying. For example, the thing that is fed here in a box, very fine nice looking stainless steel container, they are sucked along with a combination of some air let in and the vacuum that is created by this vacuum pump. The combination will create a laminar flow, and in that flow along with those molecules whose driving force is vacuum pump, the particles are fine products, they are all conveyed against gravity also, and they are finally collected here, and there will be walls on that side and this side, and you collect first and then close this wall and open this and finally collect it here in the receiving vessel. This we have discussed in other applications also, but here as a sort of continuity in pharmaceutical applications, very fine looking vacuum conveying things are connected regularly in various interstages between successive operations in a pharmaceutical sector. These conveyors are working between 70 to 100 millibar, and a typical rough pumps, even watering pumps can be connected to this. So, we have seen filtration, we have seen drying, we have seen freeze drying, we have seen distillation, we have seen molecular distillation, vacuum distillation. All these processes are now giving a lot of scope for vacuum technology to enter into pharmaceutical and chemical sector. In recent times, it is increasing more and more because of environmental concerns. So, chemicals and pharma sectors in low temperature distillations, molecular distillations, low temperature drying, freeze drying, improved filtration, it is a regular thing that is going on nowadays in high tech, particularly pharmaceutical sectors, because certain pharmaceuticals are very costly. You have to handle it under vacuum conditions properly. The safe handling of vacuum chambers, vacuum piping along with accessories or heating jackets or refrigerated condensers, they require trained manpower with a little bit of heat transfer, fluid mechanics and vacuum technology. So, this has to be thought over in pharmaceutical and chemical sectors. That is the reason we would like to train the people from chemical and pharmaceutical sectors in special operations involving vacuum technology. The standard concepts like vacuum system design, thickness calculations from mechanical engineering point of view, otherwise it will collapse. Okay. And also the piping network with conductance calculations, they all have to be done along with thermodynamic and heat transfer aspects. It is not just chemistry or pharmaceutical chemistry. So, if you do that, then the modern chemical and pharmaceutical sectors using vacuum technology will create a clean and green technology without any pollution in the environment, but creating very, very costly and pharmaceuticals with extreme purities. So, that is the advantage of vacuum operation in pharmaceutical and chemical sectors. Thank you very much.